you look on the back of your cheat sheet, you'll see a final section we haven't covered yet called the ideal gas law. It's where it's got R values circled. The good news is that if you're good at the combined gas law, overall I think you're going to think the ideal gas law is very easy. It uses a lot of the same principles while investigating the behaviors of gases. The equation that we're going to use is what's referred to in the chemistry world as Pivner, but it's pressure times volume equals moles times a constant R value times a temperature in Kelvin, of course. So here's what we'll be using and plugging all of our stuff into. There's a couple new players here in regards to what we've been using with the combined gas law. We've got N, but as the whiteboard over there in your previous notes cover, N is moles, so it's just another unit. And then the R is something different. If you look at your cheat sheet, you'll see 3 values circled for R. These are constant values. R is always one of those 3 numbers, which means the problem won't give you an R value because you can always just reference there. You don't have to memorize them. I'll give them to you on the test. You just have to know how to use them.
Pause the video, write down the question.
Our process for solving an ideal gas law problem is going to be incredibly similar to the combined gas law. We're still looking at the parameters of a certain gas and how it will behave. So let's pull the values out like we have before along with their units. The very first value I see here is 4.7 moles, followed by 19.7 kPa. And then 12.4 liters. Of course, there's a question. What does this want us to find? It says, what is the temperature? So we're looking for T. Do what we've always done. Use the whiteboard over there or the top of your cheat sheet to identify what variables these units connect to. What is the variable for moles? N. It's an N. That guy right there. For kPa, pressure. For liters, volume. You'll notice that this equation has no repeat of variables, so there's no first and second. There's only one of each. What variable are we still missing? R. All right, you're right. We are missing temperature, but that's, at least we have it accounted for. That's what we're going to solve. We need an R. Now, look at your cheat sheet at the 3 available R values. You'll see that there's 1 for atmospheres, 1 for kPa, and 1 for millimeters of mercury. And it's those pressure units that are going to select one for you. So it's not difficult. All you need to do is examine the problem, see what pressure units the problem already refers to, and that'll pick an R value for you. If we look at this problem, the pressure units that we're using is kPa. So the R value that we'll use is 8.31, because that's the R value connected to kPa. So again, it's the pressure units that will pick your R value, our constant value, to solve for the gas. Now we're ready to plug and chug. So just go straight across. My pressure is 19.7. I use parentheses to show the multiplication as usual. The volume is 12.4. Equals, the moles is 4.7. Our R value is 8.31. And the temperature we'll put as X. We need to find him. I'll simplify each side individually. On the left, 19.7 times 12.4 is 244.28. Simplify the other side. 4.7 times 8.31 times X. $39.057X. Divide by the number connected to the X on both sides. Oops. Two numbers pass. I get a resulting temperature of 6.25. What temperature units do you think this equation spits out? Kelvin. All right, gas laws are only capable of dealing with Kelvin. Very similar to the combined gas law, except there's no first and second, and you'll have to pick an R value. Looking at oxygen this time, starting with the number extraction, I got negative 13 degrees Celsius, followed by 9 liters and 50.5 atmospheres. There'll be a question. What's this one want to know? How many moles? So we're looking for the N. Remember, N is moles. Connect the units to variables. Degrees Celsius is temperature. Liters is volume. And atmospheres is pressure. Stop me if I do anything that doesn't make sense. And whenever you see that there's no repeat in variables, you know that you're going to need an R. Which R will we pick for this problem? What's the number? Find it. 0.0821, because our pressure is in atmospheres, so our R value will be 2. 0.0821. Do you see any problems that we need to fix? The temperature. Degrees Celsius is never okay. So we're going to take negative 13 and add 273 to change it to a Kelvin reading of 260 Kelvin. So watch for that. Pivnert. P is 50.5. V is 9. N is what we're trying to find. The R value we picked is 0.0821. And our temperature is 260. Simplify the left first. 50.5 times 9 is 454.5. On the other side, x times 0.0821 times 260, 21.346x. Divide by the number connected to the x on both sides. And you'll get to find out how many moles of oxygen there are in this sample. Anybody have an answer? Perfect. 21.29 moles. Questions?
They're solving both of these at the same time.
To start working on the first problem and extracting information about the chlorine gas sample, we're given values of 10.14 moles, followed by 700 millimeters of mercury, and 27 degrees Celsius. The question says, what volume will that chlorine gas have? And of course, we're going to need an R value as well. Moles has a variable of N, mmHg a variable of P, degrees Celsius a variable of T. My pressure units are mmHg. The mmHg R value is 62.4. Degrees Celsius is no good. 273 added to 27 will equal 300 Kelvin. Plug into Pivner. P is 700. V is what we're solving for. N, 10.14. R, 62.4. And our temperature was 300 Kelvin. Simplify, you'll get 700x over here. 10.14 times 62.4 times 300 will give you a big number, 189,000. Divide by the number connected to the x. I get a volume of 271.17 liters. Let's take a look at the second one. Taking a look at neon gas here. Pulling out numbers, we've got 12 moles, 3 liters, and 323 Kelvin. This problem already put the temperature in Kelvin for you. It's nice when that happens. It wants to know the pressure. And of course, we'll have to identify an R value as well. Moles is N, liters is volume, Kelvin is temperature, as we're all very good at now. Pressure is not given. It's usually the pressure units that choose the R value for you. If pressure is unknown, R can be any of your 3 values. You must make sure, though, that the answer that you express has units that match the R that you chose. So right now, since pressure is not leading us anywhere, we can pick any of the R values. Which one do you want to do? All right, someone shouted out kPa. So again, we could use any of them, but if we're going to choose 8.31, it's important to point out that our answer must be in kPa. So really, there's 3 different right answers you can get here, as long as the correct units are used. Pivnert. My P is what we're trying to find. The V is 3. The moles is 12. We decided we were going to use 8.31 for the R. And our temperature in Kelvin is 323. Simplify the left to get 3x. Simplify the right, 12 times 8.31 times 323 to get over 32,000. Divide both sides by the number connected to the x. I get 10,736.52. But the most important part of that is that it's in kPa. If you did yours in atmospheres or millimeters of mercury, convert that number. You know how to convert it. You learned that last week. You can convert kPa to the units that you used using 10,000 as your given, and it will match your answer.